Hello, everyone. Okay, hope you can hear me well. Uh, all right. Let's start. I'll share my screen. Sorry, my computer's being awkward. Okay, you should see my screen now. So welcome to webinar 3. So today we're going to talk about orbits. Honestly, I'm going to repeat myself quite a lot compared to the previous webinar. So if you have watched the previous webinars, there's not much new stuff I will be going through today. So we will be deriving the expression for the potential energy. Sorry, the potential energy. We will be drawing graphs of GR and UR for a planet with uniform density. We'll be doing the same for the hollow planet. And we will derive the expressions for gravitational energy, kinetic energy, and total energy for a circular orbit. For a circular orbit. We will talk about a binary star with two different mass stars rotating around each other, and we will try to find the period of rotation. For 6, we'll find the period of a triple star, so very similar, but now a triple star. We'll try to build a tunnel between London and New York, where trains won't go without fuel. And problem 8 is going to be Jules Verne's From the Earth to the Moon. I've done this question before in the previous webinar, so we'll talk about this book a little bit and why it is not possible to launch a person to the moon from a cannon. Maybe the answer is obvious to you, but we'll look into it with a little bit more detail. Okay, so if you think that you won't find anything new today, yeah, so just make up your mind. This is what we're doing today, and let's go. There are expressions for the potential energy of a gravitational field. So what does that mean? That means we have a massive object in space of mass, let's call it M capital, and there's a field around it. Sorry, the field is obviously in the opposite direction. So this is a gravitational field. It's a radial gravitational field. It's not uniform because it's not the same everywhere. It doesn't have the same direction, nor does it have the same magnitude. The further you are from a planet, the weaker the field. But at the surface, if we assume that the Earth is flat, at the surface, gravitational field is uniform. And we call that G, right? And that's good enough for us. When we talk about throwing a stone or even launching a projectile, that's good enough. The field has a very important characteristic. It's an energy characteristic of a field, and it's called the potential, gravitational potential of the field. So the question is, what is the gravitational potential of the field at point P? What is the potential, at that point? What does that even mean? Potential is the gravitational energy per unit mass. Potential is the gravitational potential energy divided by mass. So basically, asking what is gravitational potential is how much potential energy does something have if it's placed at that point. But we know the gravitational potential energy is mgh. But that only works for a uniform field. Right. GPE is no longer mgh. Okay? Because gravity is not uniform, the field is not uniform. Is not uniform. Because field is not, well, that is the reason. And there's H. We always, when we did MGH, we said mg delta H, right? It's mg delta H. That means that we always took with reference to something. It's like, what is the gravitational potential energy of this thing, right? And you say mgh, but what is H? Is it from the table? Is it from the floor? Is it from the ground? Is it from the center of the earth? By taking different H's, you have different results. But here, we need the gravitational potential energy. And gravitational potential energy is actually, it's the other way around. Gravitational potential energy is potential times mass. So the potential is the definition. So gravitational potential is the work done per unit mass when moving a point mass from infinity to that point in the field. So that's what it is. So imagine you are at infinity. How much work do you need to do to arrive to point P? And if you divide that work by your mass, you will find the gravitational potential at point P. Okay, potential. So potential at point P is the work per mass. Does everything make sense so far? On a scale of 0 to 10, maybe? Oh, wow. Okay. Good. And well, we need to find the work. So let's say it's the potential at gravitational potential at point P. So let's say you are moving from infinity. So what is the work done? Well, let's say you're moving along this line. Well, why would you move along this line if you're moving along this line? This is you, and there are forces acting on you. So there's the gravitational force, which is F, and it's equal to, let's say your mass is M, G, M capital over R squared, where R is the distance. Suppose you move a small distance. You move a distance delta r. The work done, delta work, is force times the distance. Now, the gravitational field is pulling you left, and the force of the field is left. But the question is, how much work do you need to do? Okay, this is the tricky part, and honestly, I always get this wrong. This is how much work you need to do to move the ball. But you don't need to push the ball. If anything, you need to hold the ball back. So the force, the applied force that you need is actually backwards applied force is backwards. So downward work times cos of the angle between the vector f and the movement. However, because you're moving this way, and the force is applied that way. So you need to hold yourself back. So the work is going to be negative because this is 180 degrees. However, because delta R works in such a way that you are reducing from moving towards the planet, moving towards the planet means that you're reducing the distance, reducing R, reducing the distance to the planet. And if you're reducing the distance to the planet, that means that delta R is negative. So overall, you have the force times the distance, the angle. This angle is 180, so there's going to be F times delta R times cos of 180, which is -1. However, because delta R is negative, you can just take the positive delta R here. So it's going to be F minus F delta R -1, so plus F delta R. Yeah, you could say that. Work done, but then it will be positive. But the gravitational potential energy is negative. Because then you would say the gravitational potential energy would be positive in your case, which doesn't make sense. Well, the idea is that you have something at infinity and it's not moving. Kinetic energy is 0. If you just let it go, the kinetic energy will be increasing. Now, if you let it go, it will just fly past your planet and end up at infinity again. Like a comet, well, not a comet, but you can imagine it would go from infinity past the planet and back to infinity. Or if it's unlucky, it could crash into the planet. So in order to move it to point P and stop it, you have to hold it back. Does that make sense? So if I ask you, you have a hill and you have a ball at point A, and you want to move it to point B. How much work do you need to do? How much work do you need to do to move ball A to from A to point B? Well, duh, you don't need to do any work, you just let it go. But no, when we say how much work do you need to do to move from A to B, we say how much work do we need to move from A to B, assuming that it is stationary in the beginning and it's stationary at the end. Right? Because letting it go is not moving it from A to B, if you see what I mean. It's just launching it. So the correct answer, so work done moving from A to B is going to be minus mgh, where h is this height. It's going to be negative because you have to hold it back. You hold it back so it doesn't go. So here's the same thing. So there's a lot of minuses involved, and hopefully I got this right because I usually get this one wrong because I always forget one minus. Anyways, if you make the step even smaller, you can say that dw is f dr. And f, we know, is gm m over r squared. So the delta work is gm m over r squared dr. We integrate it. We started from the work, zero work, and we end up with w amount of work. And then here we start from at infinity and we end up at point R. So we integrate that. So we integrate the left-hand side, and that's going to be W. We integrate the right-hand side, and it's going to be minus G M M over R to the R. Yes. Between limits infinity and R. And that is minus GM M over R minus GM M over infinity, which is 0. So the answer is minus GM M over R. I have not made a mistake. Right, so the work is minus GM M over R. And it makes perfect sense. Work is negative, just like in the previous example where you move from A to B, work is negative. And here, work is negative. So the potential at point R, or at point P, which has coordinate R, is the distance, is work divided by the mass, which is minus gm over r, which is a beautiful result, as a matter of fact. Okay, how well do you understand the derivation? Do you think you would be able to derive the same thing by yourself? If you just close the screen, and do you think you can do this by yourself? A yes or a no, or maybe it's on a 0 to 10. Okay. Oh, nice. Very nice. Okay, so that is the derivation of the planet. Now we need to draw a graph of the gravitational field and with some trimming. Why I don't get why it goes from F delta R to F delta R. Because you have two minuses which cancel out. Okay, delta R is a vector. We project it, but because it's delta R has to be is a negative value. How do we put it? Well, let's say like this. So delta R vector is minus delta R, where delta R is a positive scalar. Delta R is positive scalar, is a positive. Vector delta R is a vector in the negative direction, yes, because it's moving towards the planet, and that decreases the distance to the planet. That's why it's negative. Delta R itself is positive, it's just the length, but the vector delta R is negative, if that makes sense. It's a negative change in distance. Yes. The negative change. Like just like when you do, when you do when you do decay, radioactive decay, you do dN over dt is equal to minus lambda n. So where does the minus come from? The minus comes from the fact that dN is negative, because you are reducing the number of atoms, and that's why it's negative. So it's a similar thing. Delta R is negative, but it would be really inconvenient just saying that delta R is negative. So we say delta R is positive, and we just stick another minus in. Physicists sometimes do that. When you have an expression and you're like, oh no, I can't deal with negative values, you just stick an extra minus in and assume that the value is positive. Okay. That's why some mathematicians don't like physicists. Right, so problem 2. Draw a graph of GR and UR for a planet with uniform density. So that's actually a very tricky one, because, well, the beginning is really easy, because we know that this is the planet, and this is the radius of the planet. And then if we're measuring from the center of the planet, and it's the gravitational field. So this is R, the distance from the center of the planet, and this is G of R. Then this is the radius of the planet, and at this point, gravitational field is this. That's the gravitational field on the surface of the planet. Let's call it G0. And then it changes like inverse square. So proportional to 1 over R squared. That's easy. Now if you do the gravitational potential, the gravitational potential is a scalar, and it's negative, which is also important. R. So this is the surface of the planet. So let's say the gravitational potential at the surface of the planet, let's call it V0, at the surface of the planet, and then it increases. It increases as you go along. That's nice. That's easy. So it's proportional to minus 1 over R, because the expression is G of R is equal to G m, where is the mass of the planet, over r squared. So that makes perfect sense. So G0, in that regard, G0 is Gm over r squared, where r is the radius of the planet. So let's just write r is the radius of planet. R is the distance from center. So G0 surface on the surface, and V0 is the potential on the surface. See, potential on the surface. G0 is the gravity on the surface. Okay. So G0 is Gm over r squared, and V0 is minus Gm over r. Okay. The interesting bit starts. So this is the easy part. Okay. Does everything make sense so far with the graphs? We've literally just drawn the graphs. Now, the interesting part goes if you go inside the planet. If you go inside the planet, this equation no longer works, because this equation only works if r is greater or equal than the radius of the planet. And this equation, gr is equal to, oh sorry, not g, v of r is equal to minus gm over r. This only works if radius is greater or equal than the radius of the planet. If the distance is greater than the radius of the planet. Inside the planet, these two formulas don't work. So we kind of need to figure out what's going on. What happens when you're inside the planet? Well, can we work out what is the gravitational field in the middle of the planet? Can we work that out? Somebody tell me. 0, yeah, it is. Absolutely, it is 0. And so then we need to figure out the shape of this line here. Is it going straight? Is it like this? Or is it like this? So we don't know. Let's try to work out the g, because the g is the easier one. How does g change inside the planet? Well, you kind of need to remember the Gauss law and realize that if this is a thin shell, thin spherical shell, and you're standing here, this is your point P. You're being pulled, let's say, this part of the shell is pulling you that way. However, this part of the shell is pulling you that way. So F1 and F2. And it turns out, because the area, this area A2, is proportional to the distance D2 squared, of course, and well, yes. So force is proportional to the area. Yes, because the bigger the area of this bit, the more the force. The area is proportional to d squared, the distance squared. But force is also inversely proportional to d squared, which means that the force is constant. If you consider the same. So if you move left to right, F1 and F2 will not change. If you move up and down, F1 and F2 will change. So that means that the force from this section of the shell and the force from this section of the shell will cancel out. And you can take any other section, like this section and this section, and they will also cancel out. So the gravitational effect, well, the force is proportional to the mass of the shell, and mass is obviously proportional to the area of the shell. So mass of the section is the area multiplied by the thickness d, times the thickness t, and multiplied by the density of the material. So it's proportional to area. Right. So yeah, inside a spherical shell of uniform density, of course, gravitational field will always be 0. G is 0. Inside a shell, a spherical shell, G is 0. Cool. That is actually really nice. It's a really nice result. But that means, but what if you're in a planet of uniform density does not contain, is not a hollow sphere, but we can split it into shells. So let's say you are standing here, a distance r from the center. The gravitational field from all the shells that are outside this line gravitational field of all the shells that are outside this dotted line will be 0. You're standing at A. If you are inside a planet of uniform density, gravity from all shells above you, above means just further away from the center, is 0. So the gravity is such if you were on the surface of a planet of radius r small. So radius r big is the radius of the planet. So the gravity at A would be exactly the same if you were standing on the surface of a planet of radius small r. Same gravity at A. And this is a profound result. It actually, it's a really nice result. And let's see what's the gravitational field on the surface of a planet with radius r small. Well, with the gravitational field is the mass of the planet, but it's not the mass of the original planet, it's the mass of the planet m, let's call it mi. It's gmi divided by r squared. Oh, well, yeah, if you can approximate the Earth as a solid sphere, then yes. But of course, the density of the Earth is not uniform, so it's slightly off. But what is mi? Mi is the density multiplied by the volume, and volume is 4/3 pi r cubed. So let's stick that in. G rho 4/3 pi r cubed over r squared. And we have G rho 4/3 pi r. So we can see that the relationship is linear. It's a direct proportion. So G is proportional to R because everything else is a constant inside a planet with uniform density. I was really pleasantly surprised when I learned this when I was your age. So yeah, inside the planet, the gravitational field is that. So this is the relationship for a gravitational field with respect to the distance from the center of the planet. What about the what about the potential sorry, VR, of course. VR. Well, different things that we can do. So first of all, we can remember that gravitational field is minus dv dr. And that means that v is the integral of g dr with a minus. So the potential is the integral of g. So it's the area under the curve. Right? So if you integrate this is a straight line. So if you integrate that, so v is the minus integral of g rho 4/3 pi r dr, and r changes from 0 to r. No, let's not do that. Let's not introduce limits. So potential is minus, do we just integrate that? Minus g rho 4/3 pi r squared over 2 plus a constant. And to find that constant, we substitute r. So when r equals r capital, v equals minus g m over r. So we use that. So that would be minus gm over r minus equals minus g rho 4/3 pi r squared over 2 plus c. So c is g rho 4/3 pi r squared over 2 minus gm over r. Yeah, so we can substitute that into r squared, of course, because we need to substitute r squared. So yeah, that is C, and then you just density times volume, gm, to r, to multiply this by r, and you get gm over 2r minus gm over r, which is minus gm over 2r. Oh, that's beautiful. So V is minus g rho 4/6 pi r squared minus gm over 2r. And that's what you get. So it's a quadratic relationship. So it's a negative r squared Why is it negative? Shouldn't be negative. Sorry, I messed up somewhere. Just a second, let me double check. VR is minus GM over R. Three GM minus, so it must be minus 3 GM over R, and it's going to be plus. I'm not sure where I went wrong, because dr, oh, because it's the same error. Okay, I did say I make the same, because dr again, so as you go away from the center, the potential increases. So that doesn't make any sense. It has to be plus. It has to be plus here. So that would be plus, and then you just recalculate recalculate that, and there's going to be plus. There's going to be minus. So minus 3. Yeah, that makes sense. All right. Apologies. And then this would be, this point is minus 3 GM over 2R, and then the graph is like this. This is the more complicated part, okay, which is technically minus 1.5 V0. So the gravitational potential at the center of the planet is going to be 1.5 times the potential at the surface. An interesting result, at least for me. Do the same for a hollow planet. So when we say a hollow planet, we mean a spherical planet and a sphere of radius like R1. Let's call it R2. So I won't go into details, just draw the gravitational field quickly. Gravitational field and R. So of course the gravity inside the hollow part is going to be 0. This is R1. This is R2. So then it's going to increase. I don't think it's going to increase linearly. It looks like it's not. So it's going to be something like this. And then of course it's just proportional to 1 over R squared, the easy part. But this section, question mark. Is going to be, the gravitational field is going to be so let's say your distance r away from the center. The mass of the planet inside of you is going to inside going to be density 4/3 pi r cubed minus 4/3 pi r1 cubed. That's the mass, and the gravitational field is going to be gm over r squared, which is going to be g rho 4/3 pi r cubed minus 4/3 pi r1 cubed divided by r squared. Oh, no, it is linear. Apologies. Oh, no, it's not. It's not going to be linear. So yeah, because of this term. And so some shape. I'll let you to figure that out. R cubed minus, well, let's see. Y equals x minus 3 over x squared. Aha, yes, I think I see. It's going to be this kind of graph. So I made a mistake. This section is going to go like this. Okay. I'll leave it for you to prove it. So when we say hollow, it just means there's a shell with mass. Well, no, when we say hollow, it means there's a cavity inside. When we say a shell, that means it's a very, very thin shell. Could you explain the simplification of the fraction in finding C? Yes, of course. So here you have so we had this pi r squared over 2. So I need to find the common denominator. The common denominator is 2r. So I multiply this by r, and I multiply this by 2. That makes this 2, and this becomes r cubed. But 4/3 pi r cubed is the volume of the planet, and density times volume is the mass. So this whole thing, 4/3 pi r cubed, is the volume, and density times volume is the mass, and that's how I got GM. Does that? Yeah. Yeah. Sorry, I skipped this. Skip this part. So yes, this is a hollow planet. So a hollow planet with a cavity, not a shell. Planet with a cavity. Right. So yes, so it's going to go like this, G, and the gravitational potential is going to be so complicated that I don't think I'll do it. I'll do it. Okay, so I'll leave this one as it is now. Just an interesting thought that this actually changes the shape of this section, which is interesting. Okay, derive this is easier. Derive the expression for GPE, total energy and kinetic energy and total energy for a circular orbit. So it's something from the A-level syllabus. So something you might have done in school already. So you have a planet of mass m and a satellite, which could be natural or not, in orbit, in a circular orbit. That means that this is the radius r. It's traveling with velocity v, and well, first of all, there are a few things we'd like to find about that orbit. We would be interested in finding the time period of that orbit. Would be interested in finding the yeah. Well, we know that the gravitational potential energy, that's the easy part, is the potential multiplied by the mass. So which would be minus gm over r, which r is the radius in this particular case, over r. That's not the radius of the planet. Okay, sorry. R. So and the radius of the planet is r capital. So the r is the distance from the center. And gm over r small multiplied by m, which m. So that's minus gm m over r. G is minus dv dr. Yes. The interesting thing is that G is a vector, and this is a scalar. The derivative of a scalar can be a vector. Okay. Well, it's actually very easy. Imagine Google. Let's go somewhere to the mountainous region. Add. Well, imagine this is a slope. So we are on Google Earth, and this is a side of a mountain. I don't know whether it's a side of a mountain or not, but let's assume that it is. Um, let's say the height above sea level here is 200 meters, and here is 600 meters above sea level. So somewhere here you have 500, 400, 300. So 200, 300, 400, 500. Now, let's say your height is a scalar, Evan, I'll address that in a second. H is a scalar, but if you go your gradient of your height, dv, dh, dr, depends on the direction. So this way, it's a steep gradient uphill. So if you go along this route, dhdr is going to be positive. dhdr is going to be positive. If you go down the slope, dhdr is going to be negative. So the gradient of your ascent along the hill depends on the direction you choose. That means that it is a vector. So you can introduce your gradient. The gradient is the HDR. It's how much the height changes in a given direction. So in any direction you choose, the height changes differently. That means the vector of the gradient vector, is going to be different. This is height because it's a height above sea level. It's just how many meters above sea level you are. It's just like it's the okay. Let it be your gravitational energy. Gravitational energy is certainly a scalar, but gravitational energy is mgh, right? How does it work out mathematically? I'm going to multiply two vectors and get a scalar. It turns out to be the dot product operation. We're using the derivative. Well, it's called the gradient. It's called the gradient of a scalar field. So you know, like if you type in gradient, it gives you this because that is a gradient. You see, it goes from really red to orange, from red to orange, and that's a gradient. And is the amount of red in this particular case. The amount of red is obviously a scalar, but the direction in which it goes changes. So yeah. Right, so why is it negative minus dv over dr? It just makes common sense because if you're on the surface of a planet, the potential, this could be 60, minus 60, minus 40, minus 20. You see, the further you are from the center of the planet, the higher the potential. Potential increases as you go away from the center. And now the gravity is a downwards direction. Gravity points, the field points in the direction of decreasing gravitational potential energy. That's why it's minus. It actually makes a lot of sense. If you go along the field line, you reduce your potential. Okay. Does that make sense? Okay. All right, so moving on. So gravitational potential energy is minus gmm over r. Now to find the kinetic energy, we need to find the speed first. So we'll do that. Remember, g is a vector, so you have to take that into account. So gravitational gravity is a vector, and it's equal to g m over r squared multiplied by g hat. So it's the unit vector in the direction of g. And the direction of g is towards the center. So when we say g is gm m over r squared, this is the absolute value. Absolute value. It's not the direction, because in order for it to be a vector, you have to multiply it by g hat. Yeah. So when you differentiate it, yes, but you're by definition you're just taking the modulus of the vector and differentiating it, and of course that's going to be yeah, going to be like that. Derive the expression GP, kinetic energy and total energy, for a circular orbit. That's nice. So kinetic energy, we need the kinetic energy, and to find the kinetic energy we need V. To find V, well, we say that the force, the gravitational force, has to equal to mv squared over r. But the gravitational force is g m capital over r squared. mv squared over r. So centripetal force is equal to the gravitational force, because the gravitational force is the centripetal force. So m cancels, r cancels, and we're left with v is equal to v squared gm over r. And now we can calculate the kinetic energy. Kinetic energy is equal to, for kinetic energy for a circular orbit, is m1/2 mv squared, which is 1/2 multiplied by m multiplied by g m over r, which is g m over 2r. All right, so we have gravitational energy, is this, gravitational potential energy. We have the kinetic energy for a circular orbit. Now we need the total energy. Total energy is GPE plus the kinetic energy. Right, total energy is GP plus kinetic. So it's minus GM m over r plus GM m over 2r. We multiply this by 2, and this gives us minus 2 plus 1, so it's minus GM m over 2r. So interesting result. So we have the total energy, the gravitational energy, and the kinetic energy. And you can see that total energy is negative, gravitational potential energy is negative, and the kinetic energy is, of course, positive. So if we are to draw R, and this is the energy, so kinetic energy for a circular orbit is gm over 2r. So like this, kinetic energy equals gmm over 2r. The total energy is the same but with a negative sign, so it's just symmetrical. So that's total energy, which is minus gmm over 2r. And of course, the kinetic energy, gravitational potential energy is this. Gravitational potential energy is minus gm m over r without the 2. So it's 2 times bigger, so twice as negative. So, and as you can see, as the circular orbit becomes bigger, so this is the radius of the orbit. The bigger the orbit, the slower the satellite moves. That means Mars is slower than the Earth around the Sun. That means Neptune is even slower than the Earth. It seems like Neptune has such a high orbit, such a large orbit, that it has to go faster. But now, actually, no, we've shown that the kinetic energy is inversely proportional to the radius of the orbit. GPE. Oh, I just took the expression for GPE and I multiplied it by 2, top and bottom, to get this. Yes, so yeah, that's the thing. And the higher the orbit, the less gravitational potential energy it has, or so the more gravitational potential energy it has, so the closer to 0. So at infinity, so at infinity, kinetic energy is 0, gravitational potential energy is 0, total energy is 0. That's an important result. Okay. 5. Imagine a binary star consisting of 2 stars of mass m and 3m. So we have a mass of m, we have 3m, and the distance between them is d, and they spin around each other. They don't really spin. The smaller star, they don't spin around the middle, and they don't spin around. The small one doesn't spin around the big one. They spin around somewhere here. So they spin around this point. I don't know if I can demonstrate that, but I'll try. Yeah, it is the center of mass, of course. So fit orbits. So this is the Earth and the Earth and the Moon. And as you can see, the Earth actually moves as well. As the Moon goes around the Earth also rotates around a common center. So we can say that the Earth is many times bigger than the moon in terms of mass, so it's not that much, but the Earth actually also goes around a circle, just a very small circle. So this is the orbit of the Earth, and this is the orbit of the Moon. So they kind of go around their common center, around the center of mass. Okay, so well, it's kind of obvious because this is 3 times bigger, and this is so let's call it R1, or small r, and big R, the radius. So let's consider the small mass separately. So the small mass goes around a circle of radius r. And why does it go around the circle? Well, because there's a gravitational force causing it to go around the circle. The gravitational force, well, is g, m multiplied by 3m divided by d squared. And that force is the centripetal force. So on the other hand, that force is equal to m v squared over r small. So we have m v squared over r equals g m multiplied by 3m over d squared. So m cancels, and the velocity is equal to g 3m over d squared multiplied by r. All right. The next one, now we consider the second planet, the 3m planet. The 3m star. It has the same gravitational force, causing it to go around the circle of the radius r large. So we have m3m v2, let's call it v1, v2 squared over r is equal to g m3m over d squared. So 3m cancels, and we have v2 squared. Yes, v1 squared, v2 squared is gm over d squared multiplied by r. Okay. They're asking for that's for the speeds. We need the time period. So the time period for the first planet is the distance traveled divided by the speed. So it's going to be 2 pi r small divided by v1. Let's substitute that. So the time period is 2 pi multiplied by r small divided by v1, and v1 is going to be square root of 3gm over d squared multiplied by r. And we can work out r because it's the center of mass. Where is the center of mass? The x center of mass is So if this is from 0, it's x1 m1 plus x2 m2 divided by m1 plus m2. So the center of mass is going to be, okay, so x1 is 0. We are starting from here. This is 0 multiplied by m plus m2. So there's going to be d multiplied by 3m divided by 4m. So it's 3/4 d. Nice. So r small is 3/4 d. Yeah, 3/4 of the way. That makes sense. 3/4. And we can stick that in. So time period is 2 pi multiplied by 3/4 d divided by square root 3gm over d squared multiplied by 3/4 d. D cancels and 9. So it's 2 pi multiplied by 3/4 d root d over 9gm times 2. So 9 and 3 cancel. Apologies for the mess. 4 cancels. And we're left with pi d to the power 3 over 2 divided by square root gm. I wonder if that even makes any sense, but that's the time period. Yep, so we have the distance, we have the masses, perfect. Okay, running out of time. I don't, like, here, I'll just explain how you do this question. So you have 3 stars, and you need to find the time period for the orbit around them. So they all rotate around a common center. They have the same mass, and there's a gravitational force here. Well, what you need to do is figure out the gravitational force. So the radius r, so it's going to be mv squared over r is equal to the gravitational force, which is force is gravitational. The gravitational force will consist of 2 parts. There's, for every star there are 2 forces. There's F this way and F this way. And what you will need to do is find each force and then use vector addition to find the resultant force, which is F resultant of the 2. And that's how you do it. Problem 7. Tunnel between London and New York. This is a very interesting concept. So rather than imagining a tunnel between London and New York, I will imagine a tunnel between London and Sydney, or London and whatever's on the other side of London. So it's a tunnel straight through the middle. And you drop a stone. You drop a stone, and if you're allowed to ignore air resistance, it will keep accelerating. And remember that g is proportional to, because when you're inside the planet, g is proportional to the r, where is the distance. Let's not call it r, let's call it x. But also, let's say that this is x. This is the x-axis. This is 0 on the x-axis. So if x is here, g is downwards. So g is proportional to minus x. So G is proportional to minus x. Simple harmonic motion. Yes, thank you. All right. So when, yeah, so that means that acceleration is minus omega squared x. When x is r, when x is the radius of the planet, so this is r, acceleration is minus g, where g is, well, g the constant. And that means that minus g is equal to minus omega squared multiplied by r. And minus cancels, omega squared is g over r. That means omega is g over r, square root, and the time period of the oscillation is 2 pi square root r over g, which looks very familiar. What does it look like? Two pi of, yes, L over G. Exactly. It looks like the equation of a pendulum. So the time period of oscillation, so the time to go to Sydney and back, is going to be 2 pi r over G, where G is the gravitational field of the Earth on the surface, of course. And it turns out that because we know the radius of the Earth, the time to reach Sydney is going to be half t. So time to reach Australia is going to be t over 2, which is going to be pi square root. Radius of the Earth is 6,400,000 meters divided by 10. So that's cancels. 64, 8. So it's going to be pi multiplied by 800. 800 pi. So about roughly 800 multiplied by pi. 2,500 seconds, which is approximately divided by 60. 42 minutes. 42 minutes. So if you drill a hole from London to Sydney, roughly, you will be there in 42 minutes. You can jump and you will be on the other side of the Earth in 42 minutes. No, you drill and then you jump. Of course, it will take a few years to drill, a few thousand years. Now, and you need to suck all the air out. So you need to hold your breath for 42 minutes. I don't know what's harder. You will return. You will return in 84 minutes, of course. That's an interesting number because I wonder if I saw this number before. How long was the first space flight? It was 108 minutes. That's very close to what we got, 84 minutes. So it was on April 12th, 1961. Yuri Gagarin went around the Earth once and returned in 108 minutes. Let's see if there anything else it has this similar values. What's the time period period of the ISS. The International Space Station orbits the Earth every 90 minutes. 90 to 93 minutes, depending on the altitude. Interesting. So actually, it is the same time period you would get if you were launching a satellite at very, very low orbit. Because the ISS is 400 kilometers above the ground, it takes slightly longer. But if the ISS was at sea level, it would take exactly 84 minutes as well. So that's an interesting fact. So yeah, but what about New York? Well, it's in free fall, but acceleration is changing because your gravitational field is changing as you go through the middle. If you go from London to New York, of course, you need a tunnel, but it's like this. So this is London. It's not from the center of the planet, New York. But it turns out because effectively, if you go if you put a train on the tracks, the train will be going downhill. Because if you think about it, this is the surface of the Earth. This is level. This is going level. So if you go this way towards New York, you're going downhill. Downhill. So you won't be accelerating. And by the time you reach, when you reach the middle, you stop accelerating. And then as you pass the middle, you will accelerate backwards, so you will slow down. So you would accelerate for half the journey, and then you decelerate, and then you will stop at exactly New York. Of course, if you see no friction. And the journey would take you also 42 minutes. I don't know if it's a coincidence that the answer to the life, universe, and everything is 42 minutes, but certainly it is the answer to the question, how long will it take a train to travel from London to New York if the tunnel was perfectly straight? Okay. It is, yeah. But also, yeah, assuming no air resistance. You can work out the force because basically if the distance is shorter, but the acceleration is also so smaller. That's why it takes the same time. And finally, this question. I've done this in the previous webinar, so if you're welcome to watch the previous webinar and see. But effectively, what happened? The guys had a cannon, and they sat inside. So they sat inside the cannon. It's a fantastic book. It's very nice, very easy read. I loved it. I loved reading it. And they had there's a lot of physics in it. A lot of physics is wrong, but you'll be able to spot where it is wrong. So they were inside the capsule, and the cannon. There was a cannon which was a 700-foot cannon, and they shot the cannon, and they went to the moon. So your task is to show why this is not possible. You need to explain why the passengers would not survive the shot, because the acceleration would be too big for a human to handle. But you need to work out what that acceleration is. Okay, I'll leave you here. Hope this was useful. Hope you learned something new, and I'll see you next. Oh, I don't see you next week. Sorry, next week I'm meeting all of your tutors. Well, some of them. Meeting them at Oxford. So we'll be discussing you guys. All right. So see you in 2 weeks' time. The timetable of webinars is published, by the way, on the website, so do check. You're welcome. See you. See you.